We have a good understanding of graphing exponentials, so in this video, let's build an understanding of how to graph log functions. We won't spend tons of time on this idea, but I do think it's neat that we can understand how to graph logs by appealing to our knowledge of exponentials. So let's say that we were asked to graph, I'll just pick on y equals log base 2 of x. So I'm choosing a base of 2. I could have chosen 3, 4, 5, whatever. We'll just use a base of 2. And what's so neat about this is I don't dive into the graphing right away. What we actually do is we take the equation, y equals log base 2 of x, convert it to an exponential, and then we build a table of values from that. So anytime I'm asked to graph a log, I begin by building the corresponding exponential equation. Exponentials are just more familiar to us. If you're super visual like me, you may actually benefit from taking just a rewrite of that equation, moving the log to the left side, so that you'll see what I do next is just drop my base and crisscross, as we've been doing for a little while now. So 2 to the power of y is equal to x is the equivalent exponential statement to the given log statement. So this original statement is equivalent to this rewrite. And I don't know about you, but I feel a lot more comfortable understanding this rewritten equation than the original equation. So from this rewrite, let's build a table of values, and then we'll plot some points, and we'll call it good. So the interesting thing about graphing logs, probably the connection most missed, is unlike graphing exponentials and all other functions we've really done so far, I'm going to actually be choosing my y's and finding my x's, and that's going to feel a little different to us. So I'm actually going to be choosing my y's. The reason why I'm choosing y is because y is the exponent. So I can take 2 to the power of y, evaluate that, and then find my x. So I'm going to pick a couple negatives, 0, and a couple positives, just like we did when we learned to graph exponentials. The only difference, as I mentioned, is these are choices for y, whereas in the past they would have been choices for x. So now to find the corresponding x value for each of these y choices, we're just going to follow the rule of the function. Our function here says take whatever you're plugging in for y and take 2 to that power. So when I take 2 to the power of negative 2, like we talked about when we graphed exponentials, that's the same as 1 over 2 squared. So I'll just say it out loud since I'm a little tight on space. And 1 over 2 squared is just 1/4. If I plug in negative 1 as the power on 2, 2 to the power of negative 2 is the same as 1 over 2 to the first, so just 1/2. 2 to the power of 0, well, anything to the power of 0 is actually just 1. And then these last ones become a little bit more straightforward with the positive powers. 2 to the power of 1 is 2, and 2 squared is 4. So without too much trouble, we're able to generate some ordered pairs, which we can then plot. But again, if you can, compare this to the graph we did for exponentials when we learned to graph y equals 2 to the power of x, and you'll see that my table of values is exactly the same, just flip-flopped. That builds, again, that understanding that exponentials and logs are inverses, right? We flipped our x's and y's. So the ordered pairs I'll be plotting will be 1/4, comma, negative 2, 1/2, comma, negative 1, 1, comma, 0, 1, 1, and 4, 2. So I'm going to go ahead and plot those on the next page, and then we'll just summarize what we did, and that'll be about it for graphing logs. All right, so I need some space in the y direction to go all the way to 2. And then in the x direction, our largest value, I think there was 4. Okay, so again, here are the points we're plotting. When x is 1/4, y is negative 2. When x is 1/4, y is negative 2. So right about in there, this is just a sketch. Then we had when x was 1/2, the y value was negative 1. Then we had our next ordered pair was when x was 1, y was 0. When x is 2, y is 1. And when x is 4, y is 2. So maybe make sure you had those 5 ordered pairs written down. I know I just went through them out loud. And then if I connect the points here, we'll see the inverse graph of what we did together when we graphed exponentials. So this is the graph of y equals log base 2 of x. Let's just comment on the domain and range of this graph, maybe a vertical asymptote and an x-intercept, and then we should be pretty good. So the domain of a log without any transformations in the horizontal direction, the domain of a log will be from 0 to infinity. And it will never cross x equals 0, so we do use parentheses. And the range will be all real numbers, negative infinity to infinity. In the y direction, we don't have any restraints. The vertical asymptote, just like we had a horizontal asymptote for exponentials, logs have a vertical asymptote, so if it's untransformed, it would just be at x equals 0. That helps explain why the domain began but didn't include 0. And then another good characteristic to jot down, just like when we talked about exponentials, we talked about the y-intercept. Let's mention the x-intercept for logs. And that's going to be at this point right here of 1, 0. So those are just some good characteristics of a base log graph. So I'm just going to end this video by plotting the exponential we did last time with the log we just did, because I know many of you felt like that inverse relationship in Unit 1 was fairly understandable. So we understand that functions and their inverses are reflections about this line y equals x. And the exponential graph that we did last week, or I guess yesterday, was basically that shape. And then the graph that we just built together today is something like this. These are sketches, so they're not perfect. But we were able to identify that, hey, this y-intercept on the exponential flip-flops to become the x-intercept for the log. So this is the exponential, this is the log. We can see that the domain of the exponential becomes the range of the log. The range of the exponential becomes the domain of the log. So keeping those ideas from the past in mind will probably help graphing logs feel even more understandable to you. That's just a little intro. We don't need to spend tons of time graphing logs, but the cool thing is we can do it.